Hello everyone, welcome to our senior project presentation. My name is Sarah Chen and our presentation is a mobile green power source for emergency and special purposes using solar and wind power. Now to introduce the team, we have starting on the top left, we got I myself, Sarah Chen. Then we have Nat Nguyen, Nicholas Wooden, Christian Diaz, Kenneth Leung. Then going to the bottom left, we have Anthony Liu, Anne Feng, Andrew Uzeta, Karina Gonzalez, and finally Nate Lopez. For our senior design project, our team designed a mobile generator unit that uses a hybrid system consisting of both solar and wind power, along with incorporating a battery backup system. We designed the generator to fit within a typical 20-foot utility trailer that can be towed by an average pickup truck such as the Ford F-150. This feature is intended to make the unit easily accessible and usable to as many people as possible. The goal was to design a system that utilizes multiple power sources and can be transported to as many locations as possible with relative ease.
Here's our 3D model of the trailer that houses all of our equipment for this project. The design includes 16 solar panels with 6 on the top and 5 along each side of the trailer and a completely disassembled wind turbine. We were able to store the components to the wind turbine inside the trailer. The rest of the components, such as the inverter, battery, and rectifier, were also placed inside the trailer. We wanted enough power generated, i.e. enough solar panels and wind turbines, to be able to sufficiently provide power for a number of different applications, while also considering the limited space we had to work with within and on the outside of the trailer. We took inspiration from a real-life model, which we found on an online trailer dealer. I then took the dimensions of the trailer and the wall and designed it using AutoCAD. After we had our base, we needed to add some modifications to the existing trailer to support our needs. To do this, I added a shelf towards the front side of the inside of the trailer to be able to elevate our battery and inverter from the wind turbine components laid along the floor. In addition, I added posts on the inside of the trailer to be able to support the added weight of 6 solar panels on the roof. Another reason we had to add posts was to be able to open up the sides of the trailer, which allows us to utilize all the external surfaces of the trailer. I also added 2 collapsible support posts to each wing to be able to open up the sides. Inside, you can see the wind turbine components are efficiently stored to minimize the amount of space used. The solar panels along the side and the top are sunken into the walls of the trailer to allow the wiring to run seamlessly along the inside of the walls for a clean finished look along the exterior.
The development of this project was motivated primarily by the idea of providing aid in the form of power generation to areas affected by natural disasters. When we first started brainstorming for our project, there were a lot of large wildfires happening in California, as well as some pretty bad hurricanes that had recently occurred on the East Coast. These events left large communities without power for days or even weeks as emergency crews and responders worked to bring aid to these areas. We wanted to design a power source that could be easily transported to an area to provide power where needed and relieve pressure on disaster relief operations. We would need to design a system that was mobile, powerful, and didn't rely on any one source of power.
The following diagram was created using Visio and provides an overview of how the entire system is to be connected. As the diagram shows, the solar panel array's DC output will be connected directly to the charge controller, which is then connected to the battery. The wind turbine outputs AC voltage, so that needs to be rectified to DC voltage before it can be connected to the charge controller and the battery. The battery then supplies power to all of our outlets. We have DC outlets for which the voltage needs to be stepped down from 320 volts DC to 5 volts DC, because this is the typical voltage required to charge personal devices such as phones or laptops. There's also AC outlets for which the output needs to be inverted from 320 volts DC to 120 volts AC. We chose 120 volts AC as this is the typical voltage supplied to American Home, and thus it's the voltage required of most electronic devices.
Alright, so here's our wind turbine model. The template of this model comes from Dr. Hawley's Wind and Solar Power course, ECE 4875. In that class, we were given a project to create a 1.5 megawatt wind turbine, given a list of parameters like blade radius, pitch angle, rotor speed, number of blades, and other parameters. So for our senior project, the wind turbine team spent a lot of time using this model and tailored it to our design specifications. Because our power unit is mobile, we needed to design the turbine to be small enough to fit into a trailer, yet large enough to have a moderate power rating. Our turbine features a max power output of 7.5 kilowatts at 19 meters per second and is rated at 5 kilowatts at 10 meters per second. The blade radius is 6 meters. From there, we spent time upgrading the power factor to 0.88 lagging by supplying capacitive components in parallel to the induction generator. Then, we added a rectifier circuit that converts the three-phase AC voltage to a DC voltage. And lastly, we added a DC to DC step converter using a diode, MOSFET, inductor, and capacitor to raise the voltage to a value that can charge the battery adequately.
Okay, so for our solar model that we put together, we use SunPower's 435 watt modules to generate DC power. Our allotted amount of modules that the trailer could handle was 16, as said by Kenneth earlier, with the AutoCAD model. The reason we chose this module is because due to the limited amount of modules that we could put on the trailer, we wanted to choose a panel that could output as much power as possible without spending too much for each panel. So the price point for each module comes out to about $100 with a lifespan of roughly 25 years, meaning that there's a 25-year warranty and usually these panels last up to 20 to 25 years. The panel does not use microinverters, instead it's a system that would typically use a central inverter, whereas in our case we're connecting it to the battery and then we have the inverter. In Simulink, there is a block that allows us to input the array's information and it will give us the output that we need for the simulation in our system. So now Christian's going to explain how the circuit is connected, and then I'll explain the simulation results in a little bit.
We first began to attach a 17 ohm resistor in parallel with the positive and negative terminals of the PV array model in order to produce a current and voltage output at a specific irradiance. We then attached a current measurement in series with the positive terminal and the resistor to produce the current output at the specific irradiance at temperature value of 25 degrees Celsius. The current output is attached to the scope to display the DC current. A voltage measurement is attached in parallel to the resistor and connects the voltage output to the scope in order to display the voltage DC output. Lastly, in our model, using the current and voltage DC outputs, we calculated the power output for different values of irradiance while keeping the temperature constant at 25 degrees Celsius. Once obtaining the power values, we plotted the power output values versus irradiance, which shows how increasing the irradiance increases our power output.
We wanted to see the power output of our system versus each of the irradiances that could be possible in any given place in the United States. Put simply, irradiance is the amount of energy from the sun that we can measure on Earth. This value is usually measured as watts per square meter, solar irradiance. As shown in our graph, there's a linear function showing that the more sunlight there is per area, there is a relation where there would be more power that the panel can generate. For example, a place that sees sunlight many years of the day would have up to 1,000 watts per square meter in terms of irradiance, whereas Boston, Massachusetts would hover around 300 watts per square meter because, Boston's a little cloudy and, Phoenix, it's hot all the time. And yeah, so that's it for our simulation results. We can see there's a relation between power output and the amount of sunlight that an area gets.
After taking the power output, each time we increased the irradiance all the way up to 1000. We took the average value and obtained 4.23 kilowatts.
For our system, we are using the batteries based on the Fournier solar battery system, 12 kilowatt. The batteries is a high-performance lithium technology for maximum safety. It offers a comprehensive and highly efficient complete package. The voltage range 320 to 460 volt with nominal capacity is 12 kilowatt hours. Normal charge discharge power is 6400 watt and maximum charge discharge current is 60 amp. The dimensions height times width times depth is 955 times 570 times 611 millimeters and weight 176 kilogram, which is capable of attaching to the trailer in our model. In scene-scape simulating, we are using the batteries block to replicate the effects of a lithium-ion batteries in real life to build our simulation system. As the initial state of charge is 80% to 100%, the nominal voltage is 300 volt, cutoff voltage is 240 volt, and fully charged voltage is 320 volt. The rated capacity is 37.5 amp hours. Maximum capacity is 90 amp hours, and the capacity at nominal voltage is 81.39 amp hours.
When we run the simulation, the battery charges over time using a wind turbine and PV panels to provide a fully charged voltage at 320 volts. The battery model is designed to supply two 120 volt 60 Hz AC outlets. Each outlet is rated at 1800 watts. The AC current is supplied from the battery through an inverter designed to maintain 120 volt AC signal output on all of the outlets. This is achieved by using two logic switches and two inductors inside the inverter to control the output current accordingly as the state of charge varies. The series of switches are also added at the output of the inverter to reduce the power drawing from the battery by turning on and off one AC outlet or both outlets, based on how much energy remaining in the battery to prolong the battery life and protect the battery from permanent damages. All logic switches used in our model are controlled by a logic block.
So when the wind turbine, solar, and battery models were all completed, it was then time to integrate them. The battery model was originally built using a DC source to simulate the charging and discharging. So when it came to combining all the models together, all we essentially did was replace that source with the output from the wind turbine and the solar model. This slide provides a closer up view of the inverter and the AC outlets. Because our battery outputs 320 volts DC, we needed to create an inverter to invert the voltage to AC. As you can see from this graph, we were able to get a sinusoidal AC voltage of 120 volts at 60 Hertz.
So for our controller, we use MATLAB stateful function. And as you can see in the image, we use the current battery capacity as our controlling variable, which is then used to output switch controls throughout the circuit. The first thing we wanted to create logic for is for when the battery should supply power and when it shouldn't supply power. For our DC outlets, it's always connected to the battery to how minuscule the amount of power it consumes. The reason we want to control for when the battery supplies and doesn't supply power is due to batteries becoming damaged when they are discharged too much. For our AC outlets, they would be disconnected from the battery whenever the battery capacity would fall below 30%. And then it would have to wait till it's charged back up to 40% for it to be connected to the outlets again. The second control logic we wanted to do was for the outlets. Since the amount of power supply would vary in the real world, we wanted to make sure outlets that wouldn't be on when there isn't enough power to be supplied. So, when only 40% of the battery capacity was available, only one AC outlet would be on. But if the battery is above 50, both of our AC outlets can be on. When there was only one outlet on, a dangerous amount of current would go to the one that was left. So we used our controls to change the inductors, which allow us to adjust the current to a safe amount. When there was only one outlet on, a dangerous amount of current would go to the one that was left. So we used our controls to change the inductors, which allow us to adjust the current to a safe amount.
We are in need of new and innovative solutions to bringing power to populated areas. Solar-wind hybrid technology, as well as other variations of hybrid power, provide much-needed efficient, renewable systems for large-scale applications. Global climate change has led to continually increasing numbers of natural disasters. These events are often the cause of substantial power outages in populated areas and communities. The mobile generation unit that we have designed is not only useful for emergency situations, but can be used for a wide variety of applications and settings because of the system's hybrid power structure and physical versatility.
And you can see here we have listed some of the sources that we used. Thank you all so much for watching our presentation on our mobile green power source for emergency and special purposes using solar and wind power. We hope you enjoy the rest of the symposium event and hear our fellow colleagues present their projects.